All right, welcome back to STEM Online Academy. My name is Jason Masterakos. For those of you who don't know, for those of you who know me, you already know what this channel is about, right? Advanced math and physics for undergraduate students slash, you know, anything else. So we're going to get right to it today. We're going to look at a very interesting topic, actually. We're going to look at integrals with certain operators. Okay, so when integrals define operators, right? That's the title of today's stream. All right, and just to let you know really fast, we're going to cover why some integrals act like machines. Number two, why kernels and structure is important. Number three will be when operators generate ordinary differential equations. Four, the physical interpretation of this, and number five, I'll give you a summary at the end. All right, so at um, let's look at something that's very important here. I'm going to cover first, probably before doing anything else. Okay, we're going to be looking at uh, yeah, let's look at actually before getting to numbers to operators. Okay, it's really important, especially for my audience who's watching, because majority, you've taken you've taken calculus courses, right? In most calculus courses, integrals are treated as some sort of machine, right? That just turns functions into numbers, right? If, for instance, if you integrate a definite integral, right? You take a definite integral of a function of x, it should spit out a number, okay, like an actual number, all right, for a definite interval. But in advanced mathematics, physics, and engineering, right? All the applied mathematical sciences, right? Some of the most important integrals don't give numbers at all. Okay, so in real in real life circumstances, right? You'd be surprised. You would think there you'd be getting numbers all the time, right? In an applied setting, right? But it turns out most of these integrals don't give numbers at all. Okay, which is probably something you didn't know about. All right, so they actually give something interesting, right? What do you think they give? They give new types of functions. Okay, and once that happens, right, the entire problem is going to change. All right. So yes, when it comes to taking integrals, right, in the mathematical sciences, right? Uh, Most of the very important integrals don't give us numbers at all, right? They just give us functions. Okay. Now, why is that important? And how does that help us in the real world if we get functions? How can anyone conceptualize that abstraction, right? Well, the function tells us the behavior, right? That's why they're important. It doesn't give us a definite number. It doesn't give us a definite solution in terms of a number, but it does tell us that there is a certain type of behavior of this integral. And usually the way we were able to figure out the behavior is through graphing, modeling, and stuff like that, which I will show you very soon. Right? Big part of our channel, for those of you who don't know, and it's your first time watching, is modeling um, uh, mathematical behavior. Okay. All right. So let's look at why this topic matters. All right. Right. So why does this topic matter? Okay. The topic matters, right? Um, because in this idea, integrals act as operators, right? Because here we're looking at integrals being defined as operators. And it's one of the biggest conceptual jumps students face. Okay. I want to bring this up mainly because most of my audience has taken, you've obviously taken some calculus course, right? To be able to understand my lectures and streams or whatever. It's good if you have to have taken a calculus course, otherwise you'll be lost. Um, yeah, you probably haven't seen an operator before, okay? But it's good if you're seeing it now because it's going to help you um, solve any conceptual conceptual difficulties that you may be having. Even though it's not coming up in your calculus classes at the moment, if you haven't taken more advanced courses, um, it's good if you see or if you learn um, about operators, how integrals interplay with operators. They interplay with operators a lot, actually, right? Otherwise, you're going to think that all integrals give you numbers, and they don't, right? So that's one of the first conceptualizations, um, one of the first hurdles, I should say, that students are facing. Okay, and I just want to clear that up, right? Because if I don't clear that up, you're going to be thinking that integration about integration a certain way only. Okay, and that can't be further from the truth, right? So let's look at yeah. So I wanted to bring that up. That's really important. Okay, let's see what else I add here that I was thinking about. The no. Just give me a sec, guys. All right. So, why does this really matter, as I was saying, right? It's also one of the reasons, right, that differential equations suddenly seem mysterious. So quite often, when you do differential equations, right, differential equations, they can be written in terms of y double prime plus y prime equals 0 is one differential, homogeneous differential equation, right? An auxiliary differential equation, right? Because you could put it in terms of m squared plus m is equal to 0. And you factor and get the roots and do all that stuff. But the thing is, though, by doing that, um, how does it relate to operators? Well, differential equations actually act as operators, right? Anytime you have something, let me put over here, I'm going to highlight something, right? An operator, right? So if you have an operator, I'll give you a basic one here, right? So let's say I'm going to make some room here. Where should I put it? Like on the side or below? Yeah, or another page. We need another page here. So if you have an operator, let's say a differential operator. Just 1 second. So differential operator doesn't matter. It's an operator. I'm putting differential because in terms of a derivative or a differential equation, the notation will be a certain type of operator. So quite often, if you have a y, right, you know that y is equal to f of x, okay? However, though, if you have y prime, this is going to be d dx. This is a differential operator, okay? And if you had y, if you went all the way down to y to the nth prime, right? You're going to get d nth of dx. Okay, this is a differential operator notation, right? Right. So if you were dealing with differential equations, right? If you had, let's say, solving a y double prime plus y equals 0, right? This can still be the same as saying d squared uh, dx squared plus let's see here, what's y, right? Y equals 0, something of this nature. Okay, right? Just to give you some sort of intuition of how that would work. Okay. All right. Here, page. We don't need page 2. All right. So yes. Now, I was talking about all the reasons why operators are important. Okay. All right. So, uh, and today we're going to slow this down, right, and make it feel inevitable, right? So it's one of the, as I said, one of the main reasons why differential equations seem very mysterious. Okay. Now, let's talk about why from numbers to operators. Okay, so as I was saying, if you were to compute, let's say, a definite interval from 0 to 1 of f of t dt, you will get a number. And I think there's no dispute there. This can't be argued with, right? It's a fact that if you integrate a definite, you take a from limits of integration, you're going to get a number. Now, however, here's the thing though. if you were to compute something like this, for those of you who like fancy equations, I'm going to highlight this. Trying to get all you guys really excited. Right, so highlighting this. However, if you were to compute something like this is actually a Laplacian operator of f of x. Okay, that curly L is a Laplacian. So this, as I said, the key word is operator. I said a Laplacian operator of f of x. And this is an improper integral of the function k in terms of x and t. X is a position, t is time, right? Times f of t dt. Now, this output, right? If you were to compute it, if you were to compute this integral, the output will be a function of x. Okay. So that's really interesting, right? You would actually get an output that is dependent on x, not a number. Okay. So make that distinction. All right. So, and we'll give you some sort of model, and then you can, graph it or use, Desmos models or any type of, if you know software in particular, any of the programming languages can help you with that. We're going to do something like that actually. I'm going to show you not of this specific equation, not the Laplacian operator, uh, but we're going to look at a simulation. Okay, I'm going to show you a really cool simulation here. Okay, so let's go to simulation. Okay, because quite often I want to make sure it helps. It's fun because you can see the math come alive, and geometrically it helps you conceptualize what's going on, right? So let's look at this guy right here. This is what I like to call the integral operator, okay? And it's acting as a black box, okay? No, not a black box that you have on an airplane. That's not the type of black box I'm talking about here. Let me just rewind. So let's go slowly, right? So we have a function f of t on the y-axis, t on the x-axis, right? This is an input signal of f of t. Okay, so an integral operator, the application of that would be in terms of signals, right? Any type of signal processing and stuff like that, that's where it's applied. And you can see the integral operator from f of t and t-axis, the input signal, becomes an output function. Okay, so let me show you again. All right, this integral is no longer a number, as you can see, right? The leftmost curve there, function, is no longer enough. Originally it was a function, right? Input function f of t. But when you apply the integral operator on that function f of t, right? The output, right? The output is now it's a transformation, right? So again, the integral is no longer a number; it is a transformation. Okay. Now, you're probably thinking, yes, Jason, this is geometrically very cool and graphically really cool too. It's helping you understand, right? Right. Now, how would that look like mathematically, right? Well, if we were to go back, right, we would just say, you see this integral right here, right? This one right here that I've labeled, right? This guy here. This would be our integral operator, and I'd say that, and I define it as I as a function of some function, right? I as a function, I being the integral operator, okay? And then inside of that function would be, let's say, f, I won't say f, I'll use a different one, g of t, right? So I can say here, for instance, that one that we were looking at, the integral operator, right? So note, put here, note, I had I as a function of g, right? So let's say we had I, right? I have I, integral operator, I as a function of g, as a function of x, for instance, right? And then this would be equal to our integral, okay? So our integral of the model that I was just showing you, right? You have to be careful what's one it is. Okay, so I want to use a different color, otherwise it's not looking good. Okay, this guy here, of f of t, because our signal was f of t, as a function of t. Okay, and it's not a definite interval, but here it is, something of this nature. Okay. All right, so we've looked at that. Let's look at another situation, right? Right, so that was when we're talking about numbers going to operators. Okay, let's look at what a kernel really is. Okay, now referring back to when I was talking about from numbers to operators, this function here that I'm going to highlight, okay, this k, capital K as a function of x and t, okay, this is called a heat kernel, okay, and tells you how the values at different points interact, okay. That's what the heat kernel does. It tells you how values at different points interact, and they have a lot of applications, okay, right? So this has a lot of applications in geometry and in physics actually, okay. Obviously in physics because it's heat kernel, right? So yeah, if any of you know thermodynamics, you would make that connection. So this is a heat kernel function. Let me show you how that would work. Okay, so let's give me a sec. I'm going to go back to our simulation here. We're going to look at this one. I think this was the one. Yes, so here's a heat map of how the t values will influence each value of x. Okay, so you can see you have the t-axis, yeah, the t-axis on the y-axis here, the x-axis on the, obviously the x-axis, the horizontal axis. And you can see that this heat map is showing something very interesting. Now, I know this is not a live stream, but I'm going to make you think for a moment. What do you think the heat map is doing? What is the heat map doing? It shows how each t value, okay, let's be very careful. Right? What does it show? It shows how each t value contributes to each throughout the kernel, right? So again, let me play this again. It's not exactly obvious, and you've probably have never seen a graph of this nature before, right? You've seen bar graphs. Those are the easiest type of graphs. You learn them very young, actually. Anyone can understand bar graph. But the point is that blueprint there, um, that's just like, you can think of it as having almost like a background radiation almost, right, of the heat kernel function. That green, um, the green, light yellow, dark green grid at the background of the bar graph, okay? It's almost acting like it's some sort of radiation print. So the brighter equals stronger influence on the heat kernel, okay? Let me show you again, all right? So again, right, you can see the brighter spots of the graph here, right, is going to have stronger influence on the function, the kernel function, k, capital K as a function of x and t. And the heat map also shows how each t value is contributing to the function, okay? So watch carefully, right? So you're going to see that how each t, right, t value contributes to each function throughout the function capital K as a function of x of t. Okay, so again, I'm going to show you here, fix x, and you can see that our column shows all t values influencing that x, right? So we fix x is going to show all t values influencing x, and throughout the heat kernel K of x as a function of t. Okay, hope that makes more sense conceptually, what is happening here with kernels and stuff like that. Okay, especially when it comes to heat kernels. Now you know this notation, what it means quite often. Quite often with functions, they're just generalizations. Capital K is a function of x and t. usually that has only that's not a generalization. It's specific. Usually it defines the heat kernel. Okay, all right. So and heat kernels are very interesting. As I mentioned, they encode geometry, physics, and all sorts of applications depending on the problem. And you don't just choose kernels randomly; they come, from structure. Okay. All right. Let's look at where are we? Oh yes, why differential equations appear. Okay. Yes, why do differential equations appear? So here's a key insight, right? When you have an integral operator, okay, it has symmetry or locality, right? Right? Automatically. When you have an integral operator, and it's going to have some form of symmetry or locality, right? And the differentiation will simplify it, okay? You automatically have to apply differentiation when you have these operators. I'm going to show you what I mean um, in another simulation. It won't be a graph, but it's going to show you algebraically how the operators are working back and forth, right? Right, and I'm going to show you exactly how that works, and that's how pretty much how an integral equation turns into a differential equation. Okay, right. So it's going to be very, very interesting. Okay, and another thing I want to point out too is that when it comes to um, physics, right, this happens constantly. Okay, you're going to see this interplay of operators and integrals going back and forth, right? And you have to understand the language, right? Uh, Pretty much it's a language, right? And the language is the language of differential equations. Okay. Uh, Now, as I said, they can be applied to certain areas of advanced physics, right? So you may be looking at potential fields. What's another thing? Yeah, potentials, fields, any type of field, gravitational fields, whatever it is, diffusions, right? Waves. Uh, hmm, what else? That's all I can think of when it comes to applications, right? And all of them are going to start off as integrals, right? But those integrals have major influence, okay? All right. But the differential equations are always compressed descriptions, right? That's the way I like to describe, right? The differential equation is pretty much a compressed description of these interactions, okay? All right, let me show you another model that will be interesting. Okay, let's go back. Desktop. I want to show you a model that, pretty much summarizes or, makes it easier to understand interplay between operators, differential operators, and integration. Okay, here's our last model. So we can see we have an integral expression, right? The integral expression will automatically imply a differential equation. Yes, seems a bit counterintuitive. How are we getting a integral expression to a differential equation? Well, as you can see here, we have our antiderivative equation. If I take that integral and I differentiate it, then I'm defining capital F of x as an integral of f of t. And if I differentiate both sides with respect to x, right, I get this equation right here, that capital F prime of x equals f of x. I think all of you have learned that in your first introductory calculus course. You should have learned it. If you didn't, then you're in trouble. Anyways, again, let me show you what I'm talking about here. I'm going to rewind the video. Okay, we have an antiderivative equation. I differentiate both sides of the equation. I define what capital F of x is, of the integral of f of t. I differentiate both sides with respect to x. By differentiating both sides with respect to x, integral is going to collapse into the derivative of the antiderivative is equal to f of x, right? Okay. And yes, we know that that's to be axiomatic, that the antiderivative of the derivative is a function, okay? But we can use that when it comes to solving differential equations, right? we can actually put that as a notation. Those operators, treat it as an operator in our differential equation, and then solve the differential equation just using that notation, right? Like f of x, f prime of x, f double prime of x, depending whether you want to use f's or y's, right? Because f of x is the same as y, but if you use f prime of x, it would be y prime of x, same thing, okay? All right, we're just about done. I think we're about done. Let me see. If there's anything else to cover on the menu today, we've looked at, yeah, so we've covered why some integrals act like machines, right? Kernels and structure, when operators generate ODEs, the physical interpretation, physical meaning of all these things. No need for summary. I think it's pretty self-explanatory. Okay. So as you can see, right, when it comes to all this, right, this operator first way of thinking, okay, I like to call it, was developed carefully in my book. Okay. For those of you who don't know, my book is Advanced Integration Techniques. Okay. And it's written specifically for undergraduates, okay, in university. All right. Uh, Now it can be pretty tricky, but yeah, it is a tricky book. But as long as you have a foundation in calculus and linear algebra, you're going to be fine with it, I think, anyways. But it still requires you to think out of the box in some areas. Um, and if you want to build this type of mindset, right, when it comes to thinking this way, when it comes to, um, calculus, differential equations, and all these things applied to physics, I also work one-on-one with students, right? Whether it comes to coaching slash tutoring, okay? So if you're always looking for a coach slash a tutor, right, you can always contact me. The link will be below in the description, in the YouTube description. Okay, it's always in the YouTube description. Okay, so that's all I wanted to say. And uh, just one last thing: the goal is not to memorize methods, right? It's to understand the methods. Okay, if you understand the methods, that's the most important thing, and that way you know what the mathematics is doing. Okay, right? So the point of the today's lecture, I guess you could say, was to show you that you can go from structure, right, an integral structure in this case, all right, to operators, and then from operators, uh, hopefully you'll be able to understand how to deal with any type of operator, integral operators specifically. Okay. All right, that is it for today. One last thing before we go. Remember, the live shows are always on um, Wednesdays at 8 8:30 p.m. Eastern. Okay, and the streams. I'm always uploading streams. All right, with 2 times a week streams, once a week live shows. Right. Have a good day, guys. See you next time. Bye bye.